Hello, and thank you for joining me on this gentle journey. Tonight, we will slowly drift into the Andromeda Galaxy, a magnificent spiral neighbor of our Milky Way. The soft glow of billions of stars spiraling gracefully around its luminous core, where a supermassive black hole rests quietly. Let yourself float along its sweeping arms, drifting past sparkling clusters of stars and wisps of interstellar gas and dust, each carrying the mysteries of galaxies far beyond our own. Envision the gentle tug of its hidden satellites, the subtle interplay with our own Milky Way, and the vast halo of dark matter surrounding it, shimmering like a soft cosmic veil. As your mind wanders through these celestial wonders, feel your body relaxing, your breath slowing, and your thoughts becoming lighter, like starlight drifting across the night sky. If you enjoy these relaxing moments, please consider leaving a like, subscribing, and turning on all notifications so you don't miss any of our future videos. But for now, just breathe. Let your body relax, release any tension, and allow your mind to drift. Let's begin. The Andromeda Galaxy spans approximately 220,000 light-years, nearly twice the diameter of the Milky Way, making it the largest galaxy in the local group. Its sprawling spiral arms are punctuated with regions of dense star formation, glowing in subtle blues and pinks as hydrogen clouds collapse under gravity, creating stellar nurseries that will eventually light up the galaxy with new generations of stars. Beyond its visible glow, Andromeda harbors a vast halo of stars stretching over 1 million light-years, sparsely populated but holding clues to the galaxy's formation history. These faint stellar streams are remnants of smaller galaxies it has absorbed over billions of years, quietly narrating the saga of cosmic cannibalism. At its heart lies a supermassive black hole, estimated at about 140 million times the mass of the Sun, exerting a gravitational influence over the surrounding dense stellar bulge. Though invisible, its presence warps space-time and subtly affects the orbits of nearby stars, anchoring the galaxy in a slow, rhythmic gravitational dance. Andromeda's spiral arms are threaded with molecular clouds, cold reservoirs of gas, primarily hydrogen and helium, each potentially harboring the seeds of countless future suns. These clouds are often illuminated by young, hot stars that carve bright cavities through the gas, forming intricate, glowing patterns visible even in distant telescopes. Surrounding Andromeda are more than 30 known satellite galaxies, including the compact elliptical M32 and the irregular M110. These smaller companions orbit the galaxy, and some show tidal distortions, revealing the invisible pull of Andromeda's massive gravitational field over cosmic time. Interestingly, Andromeda's disk rotates at roughly 250 kilometers per second, a rapid pace that balances the inward pull of gravity with the centrifugal force of rotation. This rotation shapes the spiral pattern we observe, keeping the galactic arms coherent over millions of years. The galaxy contains over 1 trillion stars, with populations ranging from ancient red-hued stars more than 10 billion years old to newborn, blue-white stars just igniting their nuclear furnaces. This diversity allows astronomers to study star formation and evolution within a single galaxy. Its outer halo contains enigmatic globular clusters, spherical assemblies of tens of thousands to millions of stars. Some of these clusters are relics from Andromeda's ancient mergers, older than much of the disk itself, acting as living fossils that encode the galaxy's long history. Interstellar dust pervades the spiral arms, absorbing and scattering light, which gives Andromeda its patchy, textured appearance. This dust, composed of silicates and carbon-based molecules, also serves as a catalyst for the formation of complex molecules in space, including organic compounds that may eventually seed planetary systems. The gas in Andromeda exhibits complex motions, with high-velocity clouds moving in unpredictable patterns. These clouds, detected via radio telescopes, hint at past interactions with satellite galaxies and provide clues about the ongoing accretion of intergalactic material onto the galaxy's disk. Andromeda emits faint X-rays from its central region, a signature of hot gas swirling near the supermassive black hole and binary star systems, where one star siphons matter from another. These high-energy processes reveal violent interactions hidden behind the galaxy's serene spiral glow. Its stellar halo is not uniform. Instead, it contains streams and arcs from dwarf galaxies it has cannibalized. Some streams span tens of thousands of light-years, detectable only through careful star mapping, and they trace ancient orbits that no longer exist in the galaxy's visible structure. The metallicity of Andromeda's stars varies dramatically, with the oldest stars containing fewer heavy elements, and the younger stars enriched by successive generations of supernovae. This chemical layering allows scientists to reconstruct the sequence of star formation and galactic enrichment over cosmic time. Cosmic dust lanes within the arms form dark silhouettes against clusters of bright stars, creating intricate filaments that curve and twist, capturing light in ways that highlight the galaxy's three-dimensional structure and the dynamic processes shaping it. Observations show that Andromeda is moving toward the Milky Way at roughly 110 kilometers per second. Though this collision is billions of years away, it sets the stage for a future merger that will fundamentally reshape our cosmic neighborhood into a new elliptical galaxy. Andromeda's outermost stars are some of the oldest in the local group, with ages approaching the age of the universe itself. Studying these ancient stars helps astronomers understand conditions in the early universe and the formation of the first galaxies. Its central bulge is dominated by older, reddish stars, densely packed and exhibiting random motions rather than the ordered rotation of the spiral arms. This contrast between bulge and disk provides insight into different formation pathways within a single galaxy. Radio observations reveal enormous clouds of neutral hydrogen in the outer regions, forming a faint, extended envelope far beyond the visible disk. These clouds may fuel future star formation and offer a reservoir that preserves evidence of past interactions with other galaxies. The Andromeda Galaxy hosts multiple stellar streams aligned with its satellite galaxies, demonstrating that its growth is ongoing. These streams are faint, ephemeral signatures of galaxies being stretched and dissolved over hundreds of millions of years, gradually adding mass to Andromeda's halo. Beneath Andromeda's luminous spiral arms, enormous stellar nurseries glow in a kaleidoscope of colors, fueled by collapsing clouds of hydrogen and helium that compress under gravity, igniting nuclear fusion. These regions, some spanning hundreds of light-years, serve as celestial forges, crafting massive stars whose brilliant ultraviolet light shapes and illuminates the surrounding interstellar medium. Shrouded within its halo, faint streams of stars trace the remnants of galaxies consumed billions of years ago, their arcs weaving a delicate cosmic tapestry. Careful mapping reveals that these stellar ribbons are not random, but follow the gravitational contours carved by Andromeda's enormous dark matter halo, offering a fossilized map of its violent growth. Dense clusters of ancient stars pepper the bulge at the galaxy's core, each globular cluster containing hundreds of thousands of tightly packed stars. These compact spheres, some exceeding 10 billion years in age, act as living archives, preserving chemical signatures that reveal the early enrichment of elements across multiple galactic generations. Andromeda contains regions where massive binary star systems emit intense X-rays, produced when one star accretes material from its companion onto a dense neutron star or black hole. These energetic outbursts, while invisible to the naked eye, illuminate the high-energy side of a galaxy often admired for its soft starlight and spiraled symmetry. Its interstellar medium is threaded with complex filaments of dust and gas, forming intricate, lace-like patterns that obscure certain star clusters while reflecting light from neighboring luminous stars. These filaments act as both cradles and shields for star formation, influencing where and how new generations of stars emerge. Observations in infrared light reveal hidden populations of cooler stars in the disk that are invisible in optical wavelengths. These red giants and asymptotic giant branch stars contribute to the galaxy's mass and light in subtle ways, while providing astronomers with crucial information about the galaxy's evolutionary timeline. The supermassive black hole at the heart of Andromeda, though less active than some galactic nuclei, subtly affects the motion of nearby stars. Precise measurements of these stellar orbits indicate the black hole's mass, offering insight into correlations between central black holes and the overall structure of spiral galaxies. Vast clouds of neutral hydrogen envelop Andromeda far beyond its visible disk, creating an enormous gaseous halo. Radio telescopes detect these regions, revealing rotational patterns and turbulent motions that hint at both past accretion events and the continuous inflow of intergalactic material, sustaining the galaxy's star formation over cosmic time. Among Andromeda's satellite galaxies, M32 and M110 are particularly striking, each showing tidal distortions caused by gravitational interactions with their massive host. These perturbations provide astronomers with live examples of galactic influence, demonstrating how even small companions evolve in response to the gravitational dominance of a larger galaxy. The disk of Andromeda exhibits a warp, subtle but measurable, where stars and gas deviate from a perfect plane. This curvature likely results from gravitational interactions with satellites and the dark matter halo, offering a glimpse into the ongoing dynamical evolution of the galaxy over billions of years. Hot, ionized gas pervades pockets of Andromeda's central regions, radiating in X-rays and ultraviolet. This tenuous plasma arises from supernova explosions and stellar winds, forming a diffuse halo that interacts with cooler gas clouds, creating a multi-phase interstellar medium with complex physical conditions and chemical compositions. Stellar streams discovered in Andromeda's outskirts are remnants of past mergers, their stars moving in coherent trajectories that reveal the gravitational skeleton of the halo. These streams are faint but meticulously mapped through surveys, providing a narrative of galactic assembly invisible in ordinary optical imagery. The metallicity gradient across Andromeda varies, with inner stars richer in elements like iron and magnesium, while stars in the outer halo are far more primitive. This gradient informs astronomers about the distribution of supernova products over time, reflecting the layered history of star formation and chemical evolution across the galaxy. Radio observations have uncovered high-velocity clouds in the galaxy's outer regions, moving at speeds not accounted for by simple rotational models. These anomalies suggest ongoing accretion from intergalactic space or remnants of tidal interactions, highlighting the dynamic and continually evolving environment far from the spiral arms. Young star clusters often form in chain-like patterns along spiral arms, tracing underlying density waves that organize gas and dust. These formations provide a snapshot of how gravitational instabilities in the disk propagate star formation, revealing both the timing and spatial coherence of stellar birth on galactic scales. Andromeda's supermassive black hole has an accretion history largely dormant compared to active galaxies. But subtle emission from surrounding gas offers clues to periods of past activity. By studying these faint signatures, astronomers reconstruct episodes of energetic feedback that may have shaped the inner bulge's stellar distribution. Beyond the disk, faint old red stars inhabit the halo, sparsely scattered across immense distances. Their kinematics and chemical compositions serve as a record of Andromeda's earliest mergers and star-forming epochs, providing a tangible connection to the primordial universe while remaining invisible to casual observation. Nebulae within Andromeda exhibit complex morphologies, from elongated filaments to bubble-like cavities shaped by radiation pressure, stellar winds, and prior supernova explosions. These features act as markers of past star formation and feedback, offering visual evidence of the dynamic interplay between stars and their surrounding medium. Spectroscopic analysis of Andromeda's stars reveals subtle differences in elemental abundance, with some stars enriched in carbon, nitrogen, or oxygen due to past supernova events. These chemical fingerprints allow astronomers to trace the galaxy's star formation and enrichment history, revealing a layered chronology written in starlight. A sweeping halo of faint stars envelops Andromeda, stretching well beyond the visible disk, revealing the galaxy's immense gravitational reach. These remote stars, often isolated and dim, trace ancient accretion events, offering a living record of smaller galaxies absorbed over billions of years. Each orbit a lingering testament to cosmic collisions and tidal stripping. Massive molecular clouds within Andromeda's arms contain intricate filamentary structures, cold and dense, harboring the potential for star formation. Observations in sub-millimeter wavelengths reveal these clouds' internal turbulence and density variations, illustrating how gravity, magnetic fields, and residual motions from prior stellar births interact to shape the next generation of stars in their embryonic nurseries. The central bulge exhibits a subtle bar-like structure, where stars follow elongated orbits rather than circular paths. This configuration influences the movement of gas and dust toward the core, fueling both mild star formation and the supermassive black hole's accretion, while also guiding the spiral arm's overall shape in the inner regions of the galaxy. Andromeda hosts rare planetary nebulae scattered across its disk, glowing remnants of dying intermediate mass stars shedding their outer layers. These nebulae emit light in vibrant spectral lines, offering clues about stellar evolution, chemical enrichment, and the recycling of material that enriches the interstellar medium for future generations of stars. Satellite galaxies orbiting Andromeda reveal subtle asymmetries in their shapes caused by tidal forces, illustrating gravitational interactions on galactic scales. Some satellites exhibit extended stellar streams or warped disks, showing that even diminutive galaxies evolve in response to the enormous pull of their massive host, reshaping their structure over hundreds of millions of years. Spiral density waves ripple through Andromeda's disk, compressing gas and triggering sequential star formation along the arms. These waves maintain the spiral pattern over long timescales, guiding the distribution of star clusters, nebulae, and molecular clouds, and creating the visually coherent structure that makes Andromeda appear elegantly ordered despite its vast scale. Ancient stars in Andromeda's halo often display low metallicity, composed mostly of hydrogen and helium, indicating they formed during the universe's first few billion years. By analyzing their chemical composition, astronomers can reconstruct the early enrichment history of the galaxy and compare it with the Milky Way's halo, revealing differences in evolutionary pathways. High-resolution imaging uncovers dense knots of star formation embedded in dust lanes, where ultraviolet radiation from young massive stars illuminates surrounding clouds. These regions glow brightly in multi-wavelength observations, offering a striking contrast between dark, opaque dust and brilliant clusters of newborn stars, creating visually dramatic structures across Andromeda's spiral arms. The supermassive black hole at Andromeda's center exerts a gravitational influence detectable hundreds of light-years away, subtly shaping the orbits of stars in the bulge. Though less active than some galactic nuclei, careful spectroscopic measurements of stellar velocities provide precise estimates of its mass and a benchmark for studying correlations between central black holes and their host galaxies. Interstellar magnetic fields thread through the disk, guiding charged particles and affecting the orientation of dust grains. These fields influence the collapse of molecular clouds, regulate cosmic ray propagation, and create faintly polarized light detectable by radio and infrared instruments, revealing another invisible layer that structures Andromeda's dynamic interstellar environment. Faint X-ray sources scattered throughout the galaxy include binary systems where matter is accreted onto neutron stars or stellar mass black holes. These sources reveal high-energy astrophysical phenomena that coexist with the galaxy's serene optical appearance, providing insight into the end stages of stellar evolution and the variety of energetic interactions in Andromeda. Dust-enshrouded star clusters, especially those forming in dense spiral arm regions, emit infrared radiation that penetrates surrounding clouds. These clusters often contain massive stars that live brief but luminous lives, shaping nearby gas through radiation pressure and winds, sculpting the arm's structure and enriching the interstellar medium with heavier elements produced during nuclear fusion. Observations of Andromeda in ultraviolet light highlight hot, young stars concentrated along the inner edges of spiral arms. Their intense radiation illuminates surrounding hydrogen gas, causing it to fluoresce, which reveals the intricate geometry of star-forming regions and the relationship between stellar birth and the underlying density structure of the galactic disk. Outer regions of the galaxy contain diffuse streams of stars with highly eccentric orbits, likely remnants of accreted dwarf galaxies. These stellar populations provide a fossil record of the galaxy's hierarchical growth, allowing astronomers to map ancient interactions that shaped the present-day halo and understand the cumulative impact of minor mergers on galactic structure. The interstellar medium exhibits multiple phases, from cold, molecular clouds to warm ionized gas and hot X-ray emitting plasma. These phases coexist in complex patterns, interacting through shocks, turbulence, and radiation, creating a dynamic environment where energy is continuously exchanged, driving the evolution of Andromeda's gas and influencing future star formation. Stars in Andromeda's disk display differential rotation, with inner stars orbiting faster than those farther out. This velocity gradient maintains spiral arm coherence and stretches stellar streams over time, shaping the galaxy's visible structure while reflecting the underlying mass distribution, including the extensive dark matter halo that dominates Andromeda's gravitational potential. Observations of carbon-rich stars in the outer disk indicate sites where late-stage stellar evolution contributes organic molecules to the interstellar medium. These stars expel dust and gas enriched with carbon, which mixes with surrounding material, enhancing the chemical diversity of regions that may later form new planetary systems or stars. Certain globular clusters in Andromeda show multiple stellar populations with varying ages and chemical compositions, a surprising complexity for ancient, compact systems. These findings suggest that globular clusters may experience internal chemical evolution or accrete stars over time, providing insight into how star formation occurs in extreme gravitational environments. The galaxy exhibits faint, extended filaments of ionized gas stretching thousands of light-years beyond the main disk. These structures trace energetic events such as supernova-driven outflows or past accretion activity, creating a subtle halo of energized material that contributes to the chemical enrichment and energy balance of Andromeda's outskirts. Precision mapping of stellar motions reveals anisotropies in the halo's velocity distribution, indicating past mergers and accretion events. These motions, measured through spectroscopy and proper motion studies, allow astronomers to reconstruct the galaxy's assembly history, connecting visible stars with the invisible scaffolding of dark matter that guides their trajectories. Streams of ancient stars arc across Andromeda's halo, relics of dwarf galaxies long consumed by its gravity. These stellar remnants move in coherent trajectories, tracing the invisible contours of dark matter that dominate the galaxy's mass, and revealing a layered history of growth, marked by countless mergers, interactions, and cosmic accretion events. Within the galaxy's disk, compact clusters of massive stars emit intense ultraviolet radiation, ionizing surrounding hydrogen and creating glowing H2 regions. These luminous pockets act as beacons of recent star formation, their radiant energy shaping nearby gas, compressing clouds, and carving cavities that become strikingly visible in multi-wavelength astronomical images. Andromeda's core contains a dense stellar bulge, where stars follow elliptical orbits, contrasting with the circular motion in the outer disk. The tightly packed population exhibits a reddish hue, evidence of older stars formed billions of years ago, providing astronomers with a living chronicle of the galaxy's earliest evolutionary stages and chemical enrichment patterns. Tidal interactions have left faint streams of stars connecting Andromeda to its satellite galaxies. These filaments, some stretching tens of thousands of light-years, preserve evidence of past gravitational encounters, offering insight into the dynamics of minor mergers and the role of satellites in shaping the outer halo's structure over cosmic timescales. Massive molecular clouds in Andromeda's spiral arms display filamentary substructures observable in sub-millimeter wavelengths. These filaments harbor regions of high density where gravity triggers collapse, setting the stage for starbirth, while turbulence, magnetic fields, and radiation from neighboring stars influence their fragmentation and evolution, revealing the interplay of forces within stellar nurseries. The supermassive black hole at Andromeda's center exerts subtle gravitational perturbations, influencing the velocity and orientation of stars in the inner bulge. By precisely tracking these stellar orbits, astronomers can determine the black hole's mass, offering crucial data for understanding correlations between central black holes and the broader dynamics of spiral galaxies. Outer halo stars often possess extremely low metallicity, reflecting the primordial composition of the early universe. Studying these stars allows scientists to probe the conditions present shortly after the Big Bang, offering a glimpse into the universe's formative epochs and providing a comparative framework for understanding the Milky Way's own halo population. Nebulae scattered throughout Andromeda reveal varied morphologies, from bubble-like cavities to elongated filaments. These structures form as massive stars emit radiation and stellar winds, sculpting the surrounding gas, while past supernova inject energy and momentum, creating visually complex regions that trace the ongoing transformation of the interstellar medium over millions of years. Clusters of red giant stars in the outer disk glow faintly in infrared observations, revealing populations often invisible at optical wavelengths. These older stars contribute significantly to the galaxy's mass and luminosity, while their distribution offers astronomers clues about the formation and migration of stars across Andromeda's extensive spiral arms. Stellar streams found in Andromeda's halo provide direct evidence of hierarchical growth as dwarf galaxies are tidally disrupted and absorbed. By mapping the trajectories, composition, and density of these streams, astronomers can reconstruct past interactions and refine models of how massive spiral galaxies assemble and evolve through cosmic time. Interstellar dust pervades Andromeda's spiral arms, absorbing and scattering starlight to create intricate shadows and silhouettes. These grains, composed of silicates and carbon compounds, act as sites for molecule formation, contributing to the chemical enrichment of the galaxy and influencing subsequent star formation while producing visually stunning dark lanes against luminous star clusters. High-energy X-ray sources pepper Andromeda's disk and bulge, originating from binary systems where matter is transferred onto neutron stars or black holes. Observing these energetic phenomena illuminates the extreme endpoints of stellar evolution, highlighting dynamic interactions hidden from visible light and demonstrating the coexistence of violent processes alongside tranquil stellar populations. The outermost stars in Andromeda's halo are sparsely distributed, yet reveal critical kinematic patterns. Their velocities and orbital eccentricities trace the galaxy's gravitational potential, offering insight into the distribution of both luminous and dark matter, and helping astronomers model the unseen structure that governs the motion of billions of stars across the galaxy. Vast regions of ionized gas extend far beyond the visible disk, energized by supernova explosions and stellar winds. These glowing envelopes form a diffuse halo that interacts with cooler molecular clouds, mediating energy and momentum transfer throughout the galaxy. and revealing how feedback mechanisms operate on scales of tens of thousands of light-years. Carbon-rich, asymptotic giant branch stars eject vast quantities of dust and gas into the interstellar medium, contributing to the chemical diversity of Andromeda. This material, enriched in carbon and heavier elements, mixes with molecular clouds, seeding potential future stellar systems and influencing the composition of subsequent generations of stars across the spiral arms. Spectroscopic surveys reveal subtle gradients in elemental abundances across Andromeda, with heavier elements concentrated in the inner disk and bulge, while outer halo stars remain metal poor. These chemical variations record the sequential enrichment of the galaxy over billions of years, reflecting supernova contributions, star formation rates, and the accretion of external material from past mergers. Radio observations detect faint neutral hydrogen clouds beyond the luminous disk, forming an extended envelope influenced by the galaxy's gravity. These reservoirs provide fuel for ongoing star formation, trace past interactions with satellite galaxies, and illuminate the complex interplay between baryonic matter and the vast, invisible dark matter halo enveloping Andromeda. Filaments of hot plasma threaded through the disk shine in X-ray wavelengths, energized by supernovae and high-velocity stellar winds. These structures trace the flow of energy within the galaxy, revealing a multi-phase interstellar medium in which gas, dust, and radiation interact, shaping both the dynamics and chemical evolution of Andromeda's spiral arms. The warp observed in Andromeda's outer disk reflects gravitational interactions with satellites and the surrounding dark matter halo. Stars and gas deviate slightly from a flat plane, producing a subtle curvature detectable through careful mapping. This structural feature offers a window into the ongoing dynamical evolution of the galaxy and the influence of its massive environment. A luminous bridge of stars and gas connects Andromeda to several of its dwarf satellite galaxies, tracing gravitational interactions that span millions of light-years. These tenuous filaments reveal the ongoing accretion of material, demonstrating how massive galaxies continue to grow by assimilating smaller companions while leaving behind faint, elegant streams of stellar remnants in their wake. Clusters of blue supergiants blaze across the spiral arms, their immense luminosity outshining entire star-forming regions. These stars are short-lived, burning through nuclear fuel at astonishing rates, and their intense ultraviolet radiation ionizes surrounding gas, sculpting cavities and illuminating intricate nebula structures that showcase the galaxy's vibrant and energetic stellar ecosystems. Andromeda's outer halo contains stars with highly eccentric orbits, evidence of past mergers with irregular dwarf galaxies. These stars act as fossil traces of gravitational interactions, preserving kinematic information that allows astronomers to reconstruct the timing, mass, and trajectory of the galaxies absorbed into Andromeda's vast stellar envelope over billions of years. Infrared observations uncover swathes of cold dust interspersed within the spiral arms, invisible in optical light. This dust shields nascent stars from harsh radiation, fosters molecular formation, and contributes to the chemical enrichment of the galactic disk, providing a foundation for future star formation while adding texture and depth to Andromeda's visible structure. High-resolution spectroscopy of Andromeda's central bulge reveals subtle variations in stellar velocities, indicating complex orbital patterns and anisotropies. These measurements illuminate the interplay between the supermassive black hole, the dense stellar population, and the gravitational influence of the surrounding disk, offering a detailed portrait of the galaxy's inner dynamical architecture. Globular clusters orbiting far from the disk show remarkable diversity in age and metallicity, reflecting Andromeda's hierarchical assembly. Some clusters predate the formation of the main disk, while others were likely captured during minor mergers, providing living evidence of the galaxy's layered formation history and the ongoing accretion of stellar systems over cosmic time. Ionized gas filaments extend above and below the plane of the disk, forming a diffuse halo visible in X-ray and optical emission lines. These structures are energized by supernovae and stellar winds, demonstrating the galaxy's multi-phase interstellar medium and the movement of hot gas through gravitationally bound regions far from the luminous spiral arms. Andromeda hosts numerous faint satellite galaxies, some of which exhibit tidal distortions or elongated morphologies caused by gravitational interactions. These satellites provide a laboratory for studying the effects of a massive host galaxy on the structure, kinematics, and star formation histories of smaller companions, revealing the delicate balance of forces shaping galactic neighborhoods. The distribution of neutral hydrogen clouds across Andromeda's outer disk forms a complex pattern of filaments and clumps. Radio surveys detect these structures, showing how gas inflows, tidal interactions, and turbulence combine to create a dynamic reservoir that can feed star formation while tracing past gravitational encounters across the galaxy's extended periphery. Dense star-forming knots within the spiral arms reveal chain-like arrangements along underlying density waves. These clusters of newborn stars illuminate the gas around them, producing colorful nebulae while offering insights into how spiral structure governs the spatial organization of stellar birth across vast regions of the disk. Andromeda's supermassive black hole influences more than just its immediate surroundings. Its gravitational pull subtly affects stellar motions hundreds of light years away, creating measurable orbital precessions. These effects allow astronomers to estimate the mass and influence of central black holes in spiral galaxies, refining our understanding of galactic nuclei and their role in galaxy evolution. The outer halo contains extremely old red giants, whose compositions reflect the primordial elements of the early universe. Their low metallicity and spatial distribution provide a fossil record of ancient star formation and accretion, offering a direct glimpse into conditions during the universe's first few billion years and the initial assembly of massive spiral galaxies. Subtle warping in the outer disk arises from gravitational interactions with satellite galaxies and tidal forces exerted by the dark matter halo. This deformation manifests as deviations from a flat plane, providing astronomers with clues about the dynamic influence of unseen mass and the long-term evolution of the galactic disk's structure. Planetary nebulae scattered across the disk trace the late evolutionary stages of intermediate mass stars. Their glowing shells of ionized gas expand over thousands of years, enriching the surrounding interstellar medium with heavy elements and offering a colorful map of stellar death and chemical recycling within Andromeda's spiral structure. Carbon-enhanced asymptotic giant branch stars expel large amounts of dust and enriched gas into the interstellar medium, contributing to the chemical diversity of Andromeda. This material blends with surrounding molecular clouds, seeding regions for future star formation and enhancing the elemental variety of subsequent generations of stars across the disk. Extended X-ray emission arises from hot gas in the bulge and inner halo, energized by stellar winds and past supernovae. These high-energy signatures provide insight into the energetic environment surrounding the central black hole and dense star clusters, revealing dynamic interactions otherwise invisible at optical wavelengths. Stellar streams originating from disrupted dwarf galaxies form narrow arcs in the halo, acting as visible remnants of Andromeda's accretion history. Their composition, orbital dynamics, and alignment offer a blueprint of past mergers, enabling astronomers to reconstruct the sequence and scale of galactic growth events that contributed to the present structure. Faint, diffuse emission in the galaxy's outskirts reveals ionized gas extending far from the main disk, observed in optical and ultraviolet wavelengths. This gas indicates past energetic events, including supernova-driven outflows and tidal interactions, while tracing the chemical and kinetic history of the material beyond the visually prominent spiral arms. Subtle chemical gradients across Andromeda's disk show heavier elements concentrated in inner regions, with outer stars retaining more primitive compositions. These variations reflect the sequential enrichment from successive generations of stars, the inflow of external gas, and the cumulative impact of past mergers, providing a layered chemical record of the galaxy's complex evolutionary history. Vast arcs of hydrogen gas extend far beyond Andromeda's luminous disk, detectable through radio observations, forming a tenuous, sprawling envelope. These clouds are influenced by both gravitational interactions with satellite galaxies and inflowing intergalactic material, creating a dynamic reservoir that replenishes the galaxy's star-forming regions and subtly shapes the rotation and structure of its outermost spiral arms. Clusters of luminous supergiant stars pierce the spiral arms with brilliant light, their intense ultraviolet radiation ionizing surrounding hydrogen clouds. These massive stars are short-lived, yet their energy sculpts nebula shapes, carves cavities, and triggers secondary star formation, producing radiant regions that stand out vividly against the broader glow of Andromeda's sprawling disk. Satellite galaxies such as M32 and M110 reveal evidence of tidal stripping, with outer stars pulled into faint streams tracing their past orbits. These gravitational interactions illustrate the subtle but persistent influence of Andromeda's mass on smaller companions, providing insights into the long-term evolution and eventual assimilation of these dwarf galaxies into the larger spiral structure. In the inner disk, dense concentrations of young stars illuminate surrounding dust clouds, producing colorful multi-wavelength nebulae. These regions display intricate filamentary structures shaped by stellar winds and radiation pressure, offering a visible testament to the energetic environment of star formation within the galaxy's tightly wound spiral arms. Andromeda's stellar halo contains stars on highly elongated orbits, relics of ancient mergers with smaller galaxies. Their trajectories and velocities, mapped through spectroscopy, reveal the gravitational architecture of the halo and allow astronomers to reconstruct the galaxy's complex accretion history over billions of years. Dense molecular clouds in the spiral arms fragment into filaments where star formation ignites, guided by gravity and magnetic fields. Observations reveal varying densities and turbulence within these filaments, demonstrating how environmental factors regulate stellar birth and influence the spatial arrangement of young clusters across Andromeda's luminous arms. The supermassive black hole at Andromeda's core, while relatively inactive compared to quasars, subtly governs stellar motion in the bulge. Measurements of orbital velocities near the center provide a precise estimate of its mass, confirming correlations between central black holes and galactic structures, while illustrating the gravitational influence that extends outward across hundreds of light years. Ancient, low-metallicity stars populate Andromeda's halo, offering a fossil record of early star formation. Their chemical compositions, primarily hydrogen and helium, provide clues about the primordial universe, allowing astronomers to compare the formation histories of Andromeda and the Milky Way, and understand differences in their respective halo populations. Filaments of hot X-ray emitting gas rise above and below the disk, energized by stellar winds and supernovae. These structures reveal the multi-phase nature of the interstellar medium, illustrating the movement of energy and material across different components of Andromeda, and offering insight into the interactions between stellar evolution and galactic-scale gas dynamics. Tidal interactions have stretched streams of stars into narrow arcs, preserving evidence of dwarf galaxies absorbed by Andromeda. These stellar trails reveal the mechanics of minor mergers, mapping both the paths of captured stars and the gravitational influence exerted by the galaxy's dark matter halo over extended timescales. Infrared observations uncover populations of red giant stars concealed behind dense dust lanes. These older stars contribute significantly to the galaxy's mass and luminosity, while providing astronomers with clues about the formation, evolution, and migration of stars within Andromeda's expansive spiral arms, revealing hidden layers of stellar structure. Subtle warps in the outer disk result from gravitational interactions with satellites and dark matter asymmetries. These deviations from a planar structure, detectable through careful mapping of star positions, offer a window into the ongoing dynamical evolution of the galaxy and the influence of surrounding mass on its disk geometry. Planetary nebulae scattered across Andromeda act as markers of intermediate mass stars nearing the end of their lifetimes. Their expanding shells of ionized gas enrich surrounding clouds, providing material for future star formation and producing colorful ephemeral structures visible in optical and ultraviolet observations across the galactic disk. Carbon-rich asymptotic giant branch stars eject enriched material into molecular clouds, enhancing the chemical diversity of the interstellar medium. This contribution facilitates the creation of heavier elements that later participate in star formation, gradually altering the composition of stellar populations and planetary systems, forming within Andromeda's spiral arms. Extended X-ray emission throughout the bulge and inner halo originates from hot gas, energized by past supernova and stellar winds. Observing these emissions allows astronomers to study the energetic environment surrounding dense star clusters and the central black hole, revealing dynamic processes that occur alongside Andromeda's serene optical appearance. Stellar streams in the halo provide a direct record of accretion events, tracing the paths of disrupted dwarf galaxies. Detailed mapping of these streams illuminates the mass distribution of Andromeda's dark matter halo and reveals how minor mergers contribute to the growth and evolution of a massive spiral galaxy over billions of years. Diffuse ionized gas extends beyond the disk, forming faint halos detectable in ultraviolet and optical surveys. This material, energized by supernovae and tidal interactions, records the chemical and kinetic history of outlying regions and demonstrates how the galaxy interacts with its intergalactic environment while enriching its outer halo with processed elements. Chemical gradients across the disk reflect heavier elements concentrated toward the center, while the outer regions retain more primitive compositions. These variations provide insight into Andromeda's star formation history, revealing the sequential buildup of metals, the influence of mergers and inflows, and the cumulative enrichment from countless generations of stars. Observations of neutral hydrogen clouds in the outer disk reveal an extended, clumpy envelope that traces inflow, turbulence, and tidal effects. This gas acts as both a reservoir for future star formation and a historical record of Andromeda's interactions, offering astronomers a glimpse into the ongoing evolution of its extensive spiral structure. Dense arcs of neutral hydrogen ripple across Andromeda's outer halo, extending far beyond the visible disk. These gas streams trace past gravitational interactions with satellite galaxies and capture inflowing intergalactic material, forming a sprawling, dynamic reservoir that fuels star formation and preserves evidence of the galaxy's ongoing growth over billions of years. Bright clusters of young massive stars illuminate pockets of the spiral arms, emitting ultraviolet light that excites surrounding hydrogen gas. These luminous regions form H2 regions, sculpting nebula shapes, carving cavities, and compressing nearby clouds, creating visually striking areas where new stars are born within Andromeda's expansive disk. The supermassive black hole at Andromeda's core subtly warps the orbits of stars in the surrounding bulge. By tracking the motion of these stars with precision spectroscopy, astronomers can calculate the black hole's mass, providing a benchmark for understanding the relationship between central black holes and the structure of massive spiral galaxies. Extended filaments of X-ray emitting gas rise above and below the galactic plane, energized by stellar winds and past supernovae. These hot, diffuse structures reveal the multi-phase nature of Andromeda's interstellar medium, illustrating how energy and material circulate through the galaxy while shaping its halo and disk environment. Ancient halo stars with extremely low metallicity preserve the chemical signature of the early universe. Their compositions, primarily hydrogen and helium with minimal heavier elements, allow astronomers to study the conditions present during the first few billion years of cosmic history, offering a living window into the primordial stages of galaxy formation. Faint stellar streams encircle Andromeda, remnants of dwarf galaxies torn apart by its gravitational pull. These elongated arcs trace past merger events, mapping the invisible contours of the dark matter halo, while revealing how even small satellites contribute to the galaxy's mass, structure, and long-term evolutionary history over billions of years. Massive molecular clouds in the spiral arms fragment into dense filaments where star formation ignites. Turbulence, magnetic fields, and radiation from nearby stars influence how these clouds collapse, producing clusters of newborn stars that illuminate surrounding gas, creating glowing, intricately shaped regions that highlight the ongoing cycle of creation within Andromeda's luminous arms. Andromeda's central bulge contains an unusually high density of older, red-hued stars whose random orbits contrast with the orderly rotation of the disk. This stellar concentration provides a living record of the galaxy's early formation, preserving chemical signatures that reveal how star formation and enrichment unfolded in the first few billion years. Filaments of ionized gas stretch across Andromeda's halo, glowing faintly in ultraviolet and optical light. These tenuous structures are energized by past supernova and stellar winds, carrying both energy and enriched material far from the disk, and offering a subtle, luminous trace of the galaxy's dynamic and chemically evolving environment. Andromeda's spiral arms host tightly bound clusters of massive stars, whose intense ultraviolet radiation shapes surrounding gas clouds into intricate, glowing nebulae. These clusters act as both creators and sculptors within the galaxy, triggering secondary star formation while illuminating the structure of the arms, revealing the interplay between stellar energy and the interstellar medium. As our journey through the Andromeda Galaxy comes to a close, allow yourself to sink even deeper into relaxation. Feel the gentle pull of its spiral arms fading softly into the vast darkness, while the glittering clusters of stars leave a trail of calm across your mind. Let the quiet presence of interstellar clouds, distant satellites, and the immense halo of dark matter wrap you in serenity, as if the universe itself is cradling you. Feel your thoughts gently fading, your muscles softening, and your breath flowing naturally and effortlessly. Rest here, fully supported in this safe and serene cosmic space. If you enjoyed this relaxing moment, please consider leaving a like, subscribing, and turning on all notifications so you don't miss any of our future videos. But for now, let your body relax, release any tension, and allow your mind to drift. Good night and sleep well.